So for some textbook cases one can see what it is, and we will take one such textbook case. We will take the case of the Laplace equation with Dirichlet boundary conditions. So essentially we are looking at and a 2-dimensional case, dou square phi by dou x square plus dou square phi by dou y square equal to 0, and we have a domain. The boundary conditions are given, and we can divide this into grids like this, and as many as we wish. The finer the grid, the more accurate will be the solution. And for this particular case we are assuming that we have constant spacing delta x here and a constant spacing delta y. Because these are boundary conditions, that means all these boundary points are known, and it is only the interior points here are unknown. Okay, so we can convert this using central differencing into some a phi equal to b, and we can decompose this a into d minus e minus f, and from that we can attempt to solve this using either Jacobi method or Gauss-Seidel method or the SR method by specifying the value of the over relaxation factor. Okay, so for this particular case we can construct the iteration matrix, and we can for each case we will have a different iteration matrix, P Jacobi, P Gauss-Seidel, and P Gauss-Seidel SOR, in which the iteration matrix depends on the value of omega. Okay, so each of them have their eigenvalues. Okay, so for this particular case, for the Laplace equation with constant spacing and Dirichlet boundary conditions, we can show that the eigenvalues of for the Jacobi method are given by 1/2 of cosine L pi by m plus cosine m pi by m where L and m are the indices in the x and y directions. Okay, so they take values from 0 to m minus 1, where m is the number of divisions in this direction and this direction. So we are looking at a square thing, and then we are looking at equal number of divisions on both the sides. So these are, they are going from okay, from 1 to m minus 1 number of iterations and eigenvalues. Okay, so you have so many eigenvalues, and this we can if you what is of interest is not all the set of eigenvalues, but only the set, the maximum eigenvalue, and the maximum eigenvalue occurs when L is equal to 1 and m is equal to 1 because in that case you can see that the maximum value of L or m is m minus 1. So this is only going to go between 0 and pi. Okay, so within that the maximum value will occur when this is equal to close to 0. Okay, so the lowest value of L and M will give you the maximum value of this. So when L is equal to M equal to 1, then we get the maximum value, and that is equal to cosine pi by M. So this is 1 plus 1 2, so this cancels out with this. So this is the spectral radius of the iteration matrix obtained by applying the Jacobi method to the Laplace equation with uniform spacing, and here M is the number of divisions in the x direction and y direction. And what we see is that, as we can see from here, as M increases, then spectral radius for the Jacobi method approaches 1. Okay, and as spectral radius approaches 1, then the convergence rate decreases. Okay, why? Because we have said that epsilon k is equal to rho k times epsilon 0, okay, for long values of k, roughly speaking. So if rho is of the order of 0.8, then per iteration the error is reducing by a factor of 20%. If rho is 0.9, it is only reducing by 10%. If it is 0.99, per iteration it is reducing only by 1%. Okay, so as the number of divisions increases, then cos pi is approaching closer and closer to 1, and as this approaches closer and closer to the 1, the error reduction factor per iteration is going to decrease. So this is something that we have to pay the penalty when we go to the larger and larger grids, of not only the number of multiplications that are required, number of multiplications in this remains the same, but the rate of convergence will be decreasing in this. So that is one of the factors that we have to consider, and we also have to do for more and more number of these rows here. Okay, so with this we can make an estimate for large M. We can write rho Jacobi as roughly equal to 1 minus pi square by M square. Okay, and if we divide this into M number here, okay, and M number, the total number of variables is M square, so that is equal to N. So that means that rho Jacobi is 1 minus pi square by N. Okay, so for this, the number of iterations, that is the number of additional iterations, let us put this as additional iterations, to reduce error by 1 order of magnitude. Okay, we should point out here that although we are talking about the error here, essentially we are talking about the residual is probably the better way of describing this, because error is not known, but residual is that can be something that can be computed. And if you have a phi equal to b, then and if phi tilde is the exact solution and phi k is the solution at kth iteration, then we can say that a phi tilde is equal to b because it is the exact solution, and a phi k is only approximately equal to b, and we can say that b minus a phi k is the residual, okay, so which we can call as delta, and this is by how much the this equation is not satisfied, okay, and this residual, obviously b is a constant, a is a constant, but phi k is not a constant. So this residual depends on the iteration, on the current value of phi k. So it is this residual that can be computed, because at the end of each iteration we have an estimate of the solution. So we can substitute in this and we can evaluate the residual. So that residual, when plotted against k, is something that can be plotted at the end of each iteration, and that residual would show a variation which for a convergent scheme would be decreasing like at a constant rate when you plot it on a log scale. Okay, so this residual here is not a simple quantity, it is a vector quantity, because for each equation there are n number of equations, so there are n values in this. So this column vector, and we need to plot the norm of this vector, and the norm of that vector can be either the L1 norm, which means that it is the sum of the absolute values okay, or it can be the L2 norm, which is the RMS root mean square value. So that is 1 by n of delta 1 square plus delta 2 square plus delta 3 square, like this. So any of either L1 norm or L2 norm of the given equation a phi equal to b with an estimated solution can be computed. Okay, so this norm, the variation of this norm with k is an indication of the rate of convergence. Okay, so it is this norm that we try to so the lower this value it is, the lesser is the degree of dissatisfaction of the current solution to the exact equation. So we would like to reduce this residual to a very low value, and that residual norm variation here follows the same way as the eigenvalues. Okay, so the spectral radius and the number of iterations that are required to reduce the error or the residual here is given essentially by ln of is given by minus ln 1 minus rho. Okay, and because our rho is given by this, then it is given for the case of the Jacobi method as 0.466 n, where n is equal to m square. Okay, so for the Jacobi method, for the case of the Laplace equation, with equal division in both x and y and the number of divisions being m with Dirichlet boundary conditions, the number of iterations to reduce the residual by one order of magnitude is 0.466 n where n is now the total number of variables. So if we want to reduce by the error by 4 orders of magnitude, that is we are looking at the 4th decimal accuracy, that is the kind of situation, then the number of iterations required will be 4 times 0.466, so that is about 2n number of iterations are required. Okay. Now each iteration, so that is to go from k to k plus 1, k to k plus 1 requires about 5n number of operations. To go from k to k plus 1. Okay. So that means that in order to get a satisfactory solution, we are putting the satisfactory in quotation marks, by which we mean that the residual norm has been decreased by 4 orders of magnitude. Okay. So then we need 5n 2n number of iterations, and each iteration costing 5n number of mathematical operations, that is 10 n square number of mathematical operations. Okay, so this is how we can arrive at the number of mathematical operations that are required for a given iterative scheme. This is not an exact estimate, firstly because we are looking at the asymptotic rate of convergence, that is when this error reduction factor gets into a logarithmic range after some number of initial iterations. Okay. This some number depends on the spectrum of eigenvalues, and we have seen that the spectrum of eigenvalues for Laplace equation varies like this, and it is only the maximum value that is going to determine the asymptotic convergence rate. So it is only that the value that we are estimating here is the number here in this region, not this number. So if you reach this asymptotic rate of convergence only after say 100 iterations like what we have put here, then we are not counting the initial 100 iterations that are required to get into the second decimal accuracy. Okay. So this is only a rough order, but typically this is considered to be an estimate, a reasonable estimate of reaching a satisfactory solution. Okay. Reasonable estimate of the number of mathematical operations that are required for getting a satisfactory solution, and the point is that this value, this factor 10 here, maybe 20, maybe 30, maybe something like that, but it is not dependent on the number of, it is not directly dependent on the number of variables that we have. Okay. One can argue, as we are pointing out here, that as m increases, the number of eigenvalues obviously increases, and there are more and more number of eigenvalues having larger and larger things, so that the falling into the asymptotic convergence rate becomes slower and slower, and we need to have more and more number of operations that are required before we get into this asymptotic convergence rate. So we can make all those kind of arguments, and because of all those arguments, this is only a reasonable estimate. Okay. So this is not an exact estimate, but one can say that for the Jacobi method, for a Laplace equation with Dirichlet boundary conditions, the number of mathematical operations is proportional to n square, where n is the number of variables. And we want to compare this with the case of the same a phi equal to b done using Gaussian elimination or LU decomposition method, which requires n cubed by 3 number of operations. So when we talk about large number of variables, in such a case this factor of 10 or 20 or 50 does not make so much difference, and we can look at n cubed and n square thing, and we can declare that the Jacobi method is superior to the Gaussian elimination method. Okay. Now we have looked at the Jacobi method, and we can also consider the Gauss-Seidel method, because even for the Gauss-Seidel method for this particular thing we have the expression for the full spectrum of eigenvalues, and in this particular case the eigenvalues for the Gauss-Seidel method are given by 1 by 4 of whole square, and from this we can write lambda max, that is equal to the spectral radius for the Gauss-Seidel method is again when L is equal to 1 and M is equal to 1, and this is given by cosine square pi by M. Okay. And in the case where M is large, this is roughly equal to 1 minus pi square by M square. I think here it is pi square by 2n. Okay, in the case of Jacobi methods, pi square by 2n here. Yeah, this is 2m square here, and in this case this is okay. So we can see that 1 minus rho for the Jacobi method is pi square by 2 m square. For the Gauss-Seidel method it is pi square by m square. Okay, so that means that the factor of reduction of the residual per thing, okay, per iteration is less in the case of Jacobi method than in the case of Gauss-Seidel method, and as a result of this the number of iterations that are required to reduce the residual by a factor is exactly, okay, for this particular problem is half as much as what is required for the Jacobi method. Okay, for this particular case, that is for the Laplace equation with Dirichlet boundary conditions with constant division like this, in this particular case the number of iterations required to reduce the residual by a factor of 10 is half as much as what is required for the Gauss-Seidel method. So if it takes 2n number of iterations for 4 orders of reduction of the residual for the case of Jacobi method, in the case of Gauss-Seidel method it requires only n, and each iteration takes 5n number of operations. So instead of 10n square we will have 5n square. Okay, so for the case of Jacobi method, for the case of Gauss-Seidel method, the number of operations required is still proportional to n square with a lesser constant. So as compared to the Gaussian elimination or LU decomposition method, for the same problem of Laplace equation we have n square number of operations that are required for the basic iterative methods, and we can show through a similar kind of analysis for the case of SR method with an omega here. Then again the spectral radius will now be a function of the omega parameter, and for this particular case we can try to find that value of omega for which the spectral radius is minimum, because we want the smallest spectral radius so that the residual reduction factor is more per iteration. So under those conditions we can show that for the Gauss-Seidel SR method, the number of operations required to reduce the error is not n, but it is square root of n. Okay, for the case of Gauss-Seidel SR method, in order to get a satisfactory solution we need only square root of n number of iterations, each iteration again costing about 5n. So the total number of mathematical operations that is required is n to the power 1.5. Okay, so this is for the case of optimal SR method. So for the case of optimal SR method, where the parameter omega has been optimized so that the spectral radius is as low as possible for the case of Laplace equation, in such a case the number of iterations that are required for one order of reduction of the residual varies as square root of n. It is, whereas for Gauss-Seidel method and Jacobi method it varies as n. So in such a case the total number of mathematical operations required for the convergence varies as n raised to power 1.5 instead of 2, and that as compared to this for a direct method, this makes the SR method, optimal SR method, as a very attractive scheme. But this result here, mathematical result, is true only for symmetric positive definite matrices. So which is what we get if we take the Laplace equation or a Poisson equation and then use some central differencing kind of methods to do the Dirichlet problem. For the general case this is not necessarily true, and when you have non-symmetric matrices then this result may not be true. Okay, but even then experience shows that the iterative methods will converge, the total number of mathematical operations required will be probably significantly less than what is required for the direct methods, and as a general principle we make use of these basic methods for the solution of large system of equations like a phi equal to b. In the next lecture we will look at some methods which take advantage of the iterative methods in terms of getting to a faster convergence, but we also put in wherever possible the advantage of a direct method in order to derive combined methods which will give an overall reduction in terms of the total number of mathematical operations. So those combined methods are what we will discuss in the next lecture.